Welcome everybody to my presentation. So as said previously, today I will make an overview of our work we have performed since long time ago using this so-called DWS technology for diffusing wave spectroscopy. We apply this technique for different materials, and I will show you how we deal with these results, how we get information which are very important for this very different type of materials. But first, here I just show you this small video here, which show you here the displacement, the Brownian motion of some tracer particles, because this DWS technique is based on the motion of these tracer particles. You will see the principle for people which are not familiar with this technique. Before starting with this technique, first I have to introduce a little bit my university and our research topics here in Karlsruhe. So I'm working in the mechanical process engineering group here, headed by Professor Willenbacher, and we are located, you can see on the map here, in Karlsruhe. It's a city in the southwest of Germany, close to the French border here. And our main competences are, for instance, rheology. So we are doing classical rotational rheology. We are doing extensional rheology, also capillary rheology, and of course, microrheology. Another competence is in formulations. We design new materials. You will see here different topics. And also, more recently, we are extending our competence in printing, like screen printing and also 3D printing. So here you see our main research topics. One deals with energy materials. We improve silver paste here for solar cell metallization. Also, we design new paste for lithium-ion battery. So this is related to these energy materials. We're also working on so-called functional materials. These are materials we design based on the capillary suspensions concept. So basically, they are made of ceramics, like you see here, different ceramics membrane or printed ceramics materials here. So, and we have more common or more, I would say, common topics here related to the rheology of complex fluid. Like, for instance, we're interested in lubricant and grease at low temperature. But the topic we are talking today, and I'm working since many years now, is including biomaterials, also surfactant solutions, or biopolymer like hyaluronic acid, collagen. Also, we are dealing with bioinks, and we are 3D printing these things. This is for, would say, printing with living cells. And basically, with these materials, we are performing rheological measurements, but also macrorheology measurements. And the topic of the day will focus on this one microrheology technique, that is DWS. And I will show you again for the different systems here investigated, which information we can win from such kind of measurements. And here, the overview of my talk. So in the first part, I need to introduce you first the difference between classical or so-called macrorheology versus microrheology. What are the differences? And I will introduce the principle of so-called thermal macrorheology techniques, and also the so-called generalized Stokes-Einstein relation, and say some word about the frequency moderate range you can reach using these thermal macrorheology techniques, and also different assumptions for the validity of the generalized Stokes-Einstein relation. So this in the first introduction part, but then I will focus on different application using this DWS technique, say also some word about the theory, how is this working, and the different application. For instance, since now many years ago, we started to use this technique on worm-like marcellus solutions, and also biopolymer like hyaluronic acid and protein solutions. We investigated also thermosensitive materials. You will see what information you can get, and also a suspension. It was clay suspensions. So I would say 4 classes of different materials using this microrheology technique. So first, what is difference between Biopolymer or macrorheology and microrheology? So the microrheology, this technique probes the entire sample, whereas in microrheology, I would say mechanical properties are determined locally in a micrometer length scale. This is the main difference. Here we get information about the full sample, and here local information. And in case of macrorheology, to measure the so-called complex shear modulus here, J star, which is the sum here of J prime plus EJ double prime. J prime is the elastic module here, storage modulus, and J double prime is the loss modulus, which represents the viscosity of your solution. To measure that, we need a rheometer like this one here shown in the picture, and we have to perform so-called oscillatory shear measurements. And we need to use, depending the sample you have, the viscosity or elasticity sample, you can use cylinder geometry, cone plate, or plate geometries. And with this rheometer, the modular range you can measure is from water. So basically, you can measure viscosity of water up to solid, up to the megapascal regime here in elasticity. So a very broad modular range. What is limited, you will see later, is the frequency range. So with this rheometer, you can measure low frequencies, but you can reach only around the maximum 100 hertz in frequencies. This is the maximum frequency you can measure. Concerning the sample volume, you need milliliters of a sample volume. And if you compare to microrheology, as mentioned before, with this technique, we measure mechanical properties at the microscale. The sample volume you need is very low amount compared to macrorheology. It's in the microliter range, or at least less than 1 milliliter is enough. So this is the first advantage of this microrheology technique. And how it works, what's the principle? So basically, it's called microscale probe particle approach. So what you have to do, you have to put, like here, some microscale tracer particle into your material, and this particle will move due to thermal fluctuation. So they will have the so-called Brownian motion. And what you measure in microrheology is the motion of this particle. You have two possibilities. You can measure it by light scattering. So this is the so-called DWS technique, which I will talk today. But you can also measure the displacement of the particles optically with a video camera. This is the so-called MPT technique for multiple particle tracking, or also video particle tracking. But today focus on DWS. So basically, this motion of particles will be expressed in terms of mean square displacement, called here MSD. And from the mean square displacement of the particles, using, you will see on the next slide, some relation, we can connect this displacement to the local viscoelastic moduli J prime and J double prime. So what the main advantage of DWS technique? So first, there is no external driving force which is required to do a measurements. So basically, only the Brownian motion is enough to measure the viscoelastic properties. And because this motion, which can be expressed in terms of energy, KBT, this thermal energy is very low. So we are basically sure that we are in the so-called linear regime. So the displacement of the particles basically do not destroy the structure of your sample. This is very important. And another main advantage of DWS is that you can reach a very broad frequency range. As you can see here, you can attain the megahertz regime, so much more higher in frequency than the conventional rheometer here. We can only measure 100 hertz here. So in this high frequency regime, or very broad frequency, using DWS is also a fast measurement. So it takes around less than 5 minutes to get the full spectrum. The next slide here, I will consider two cases. First case is then when your tracer particle is added in a purely viscous liquid, like water, for instance. In that case, you have purely diffusion. In that case, the mean square displacement, if you monitor the mean square displacement, behave like a linear here dependence as a function of time, lag time. So this is a log-log here diagram. So we have this behavior here in a purely viscous liquid, and we have this relation between the mean square displacement here and the diffusion coefficient of the particles here, which is given here by this so-called Stokes-Einstein relation here. And basically, if you do these measurements here in a purely viscous liquid, you can determine the viscosity eta of your solution here, because unknown is only eta, because r is the radius of the particle you input in solution. This is known here. So this is one case, but this is not very interesting case because it's pure liquid viscous. We are more dealing, or maybe most of the sample we have investigated, they are so-called viscoelastic. They are not purely viscous liquid. So in that case, in a viscoelastic material, the variation of the mean square displacement here as a function of lag time here is given by this here curve here. You see, you have now a so-called S-shaped curve. At very low time, short time, you have the slope of 1 here. This is because here at very short time, the tracer particle is sensing the viscosity. So you have this corresponds here, the solvent viscosity, we have diffusion. Therefore, you have the slope of 1. But at longer time, the tracer particle feel the elasticity of the network. Like for instance, here you see the tracer particle is within a network. So at this would say short, also medium time here, the tracer particle feel the network elasticity. The motion of the particle is restricted. Therefore, it's flattened here. It's becoming flat, the mean square displacement. At longer time here, again, the tracer particle can escape this network and can diffuse again. Therefore, again, slope of 1. And in this long time here corresponds to the microscopic viscosity. So this is a typical MSD behavior for a viscoelastic material here. If you would deal with a pure elastic gel, no viscosity, then in that case you would come out with here an MSD which is independent with time here, which also not really happened in our case. We are dealing with such kind of materials where we have a viscoelastic response here. So this is what you measure, and basically then using this generalized Stokes-Einstein relation, which is given here, which connects the mean square displacement with the viscoelastic properties of your sample here. But you see in the formula here, the MSD is given here in frequency domain here, and experimentally you measure the mean square displacement in time domain. Therefore, after the measurements, you need to make the Laplace transform of the mean square displacement to have it the mean square displacement in the frequency domain, and then it's included in this relation, and it gives you J prime, J double prime here. This is the principle how it works, the determination of viscoelastic properties performing these microrheology measurements. And some recommendation for the tracer particle you add in the solutions. The tracer should not interact with the material. It's very important. You have to know the particle size. They should be highly monodispersed, well distributed in your sample. They also should not aggregate these tracer particles, and you need to have sufficient contrast in index of refraction to measure their motion. This is very important, would say, specification. And if you deal with aqueous solution, which was most the case in our studies, the most common used tracer particle are polystyrene particles here, with size around 1 micrometer, or would say half a micrometer particle size in diameter. We have also used titanium dioxide particles, as I will show you in the examples, but the most used are polystyrene particles. About the frequency and modular range. So first, the frequency range, as mentioned before, the advantage of DWS, this light scattering technique, is that you can cover here a very broad frequency range, up to the megahertz regime here. This is much more compared to the classical microrheology, and also to these other macrorheology technique, this multiple particle tracking technique. So this is the one main advantage of DWS, and this is also what we use, these high frequency measurements in our studies. Concerning the moduli, also elastic moduli, here J prime, for instance, DWS also can cover very broad area, would say up to 10 to the power 4 Pascal. So the material is quite elastic and is much better compared to this second macrorheology technique where we are limited around 50 Pascal here. So this is concerning the modeling frequency range. As already said, application, of course, you can study similar materials that what can be measured using conventional rheology, as a soft material or complex fluid. But what is interesting with the DWS here, or in general, this macrorheology technique, is that you can investigate very rare or precious materials. Materials which are very brittle, fragile, can be measured using macrorheology technique, and in particular, DWS. And also materials that cannot be produced in large quantities, like for instance, DNA network or like that people can produce just 1 milliliter or less. And therefore this macrorheology technique are very useful. Now some assumptions of thermal macrorheology. And for validity of this generalized Stokes-Anschauer relation, there is some assumptions which has to be done. So first one is that you should be at equilibrium. This means no external driving force or torque would say disturb the displacement of the tracer particles. This means you should have in your sample no flow or convection effect, and therefore you should be careful to make your measurements only tracking the Brownian motion and nothing else. And also the second point is that inertia of the probe particles, inertia of the fluid can be neglected. This has to be admitted also. But most important for the validity of this generalized Stokes-Anschauer relation is this continuum approximation. This means that you have to treat the fluid around the tracer particle as a continuum. This you can understand by watching here this scheme here. Basically, if you probe, would say a network with a certain mesh size C, so if you need to use, for instance, tracer particle which are much larger, for instance, that's the mesh size here. And in that case, when the tracer particle size is much larger than the mesh size, you are measuring the bulk response. So basically, in that case, macrorheology measures similar properties than bulk rheology. So this is how to say the continuum approximation. And this is happening when you are dealing with quite homogeneous microstructure. But you see on the other extreme case, for instance, when you are tracer particle and they are smaller than the mesh size, in that case, as shown here, you are sensing not, would say, the elasticity of your network, but you are sensing here the viscosity of your solvent here. So in that case, of course, then macrorheology give different results than bulk rheology. So here you have not, would say, fulfill the continuum approximation here. So this is typically what can happen when you are dealing with quite heterogeneous samples here, where you can have pores, large pores, and other region which are quite highly elastic. So heterogeneous sample, basically the macrorheology give different results than bulk rheology. This is very important to know. So let's come more in details with the DWS technique. As you can see here, it's a light scattering technique. It deals with a laser. And we use this technique to measure the high frequency viscoelastic properties of these different materials. So we use basically, you have two modes, the transmission mode or the backscattering mode. So we use DWS in transmission mode. This to, would say, characterize high frequency mechanical properties of the materials. The principle of DWS, it's light scattering technique. Basically, it's an extension of the classical DLS, dynamic light scattering technique. The dynamic light scattering technique is based on the fact that the photon is, would say, scattered once. And in DWS, we have multiple scattering here, which occurs. So basically, DWS, it works with highly concentrated fluids, and the samples you are investigating should be turbid. So you should have multiple scattering. The light is scattered multiple times before it comes out, like shown here on this small scheme here. You have the laser, you have your tracer particle added in your solution, and you see that here the photon here is, would say, scattered several times before it comes out here. But what is recorded is exactly similar than what is recorded performing DLS. It's the intensity fluctuation. So why the intensity fluctuated? It's because this tracer particle have this Brownian motion. Therefore, you have the fluctuation of the intensity. And what is important to remark is that you measure an average intensity fluctuation. This is very important. So you average the intensity. The intensity fluctuation comes from the average of all the tracer particles, not only one particle. And this is what you measure. And then using a correlator, you are building this so-called intensity correlation function. This is similar than for DLS. And here it's normalized to 1. So here you have, how to say, correlation between the particles. And then after some time here, you lose the correlation and it's a decay down to 0 here. And this intensity correlation function can be related to the mean square displacement here. And as you can see here, this is the curve I showed you before. This is the behavior of the mean square displacement within a viscoelastic material. We have this S-shaped form here. And what is very important with DWS compared to DLS is that in DWS you can measure very small particle displacement down to sub-nanometer resolution. So very small, and compared to DLS, dynamic light scattering, you can measure several nanometer displacement. So we have much better resolution in DWS. That means very small displacement means all very short time scale, down to 10 nanoseconds. So short time scale, inverse time give you the frequency domain. Therefore, we can obtain high frequencies by using DWS here. As you can see here, the frequency range here, this is now after using this generalized Stokes-Einstein relation. We calculate here J prime, J double prime from this curve here. And you see here very nice behavior of a viscoelastic material in this high frequency regime here up to the megahertz regime. So basically the conclusion is that AWS provide fast access to high frequencies, but the drawback is that you have no spatial resolution. You average the particle displacement. And yes, this is just now a picture of this DWS setup, this DWS Rheolab we bought from LS Instrument. So everything here is included in this box here. You have the laser, you have the sample holder here, you have the heating elements and the detector. Everything is included in this black box here. So this is the last version of this Rheolab here. And here you see it's quite small. It doesn't take spaces. And here you can see the different specification of this instrument here. So we have this one, but we have also the old version of this instrument here, and main of the results have been provided or done using the old setup here. So this was the first part, the introduction part. Now I will give you an overview of different application we made using this DWS technique. So the first one was dealing with worm-like micellar solution. This is a worm-like micelle here. Basically, it's composed of aggregate of single surfactant molecules here. So there's long chains here, filaments. The length can be up to micrometer. The diameter here of these micelles is between 1 and 10 nanometer. And you will see that using DWS, we provide information, also rheological information, structural information, also dynamic information for this type of materials. And this is an example comparing the viscoelastic properties, also J prime, J double prime, obtained on a surfactant system. It was this one, cetylpyridine chloride, mixed with salt here. It was sodium salicylate salt. It's a typical model system, this surfactant solution. And we see here in the full points here in black and red is what is obtained measuring this system with rotational rheology. And the green lines here is what is obtained within 5 minutes with, this was a picture of our old setup here, with our DWS instrument here. We see a very good agreement in this regime here at low frequency. The crossover J prime J double prime is quite similar in both methods, but you see that we can extend here the frequency range in DWS up to almost 1 megahertz here. This is something very important for these samples here. So basically, we can measure within 5 minutes around 7-8 decades here in frequency, which is quite impressive. So which information we get out from this rheology curve? So from, you see the first crossover here, we can calculate the relaxation time of this chain here. From this plateau here of J prime, we can read directly G0, which is called the elastic plateau module, give you information about the elasticity of the network. And using this relation here, this is G0 here. If you put G0 in this relation, you can get information about the mesh size of the system, the length of the mesh size. From the minimum of J double prime here, this gives you information about the breaking time. Specificity of this worm-like micelles chain is that it can break and recombine. So we can here determine the breaking time. But what was very important and interesting for us is from this very high frequency regime here, where we have a variation of J double prime with omega with an exponent 5/9. This corresponds to the so-called Zima regime. And at even higher frequencies here, we have a change in the slope to 3/4 slope. And this corresponds, this exponent 3/4, to internal bending modes of individual Coulomb segment. And basically from the crossover between this 5/9 slope and this 3/4 slope in this high frequency regime, using this relation here, we can determine the persistent length of the system. So LP here give you information about the chain flexibility. As you can show here, this is my network here. LP is the length here before you have the curator here. So it's chain flexibility information. So this is an important parameter. We get, normally you get LP only from neutron scattering or Sachs scattering or also dynamic light scattering. So here we get it from the just simple rheological measurements. And also from this intermediate regime here, by performing a variation in temperature and making an Arrhenius plot between here G0 divided by J double prime minimum, we can calculate the scission energy of this chain here, the energy need to cut the micelle in two, which is related to the length. So we get also information about the length of the micelles. And finally, using this relation here, we can also determine the rotation time of this chain here. This is in the fast breaking regime. And so you see, for a simple rheological measurements done in 5 minutes, we can, for this type of worm-like micelles, characterize many, around 7 to 8 parameters here. And we use this technique to investigate a so-called single surfactant system. So this was a cationic surfactant mixed with different types of salt. So we have used 2 types of salt, some non-penetrating salt versus penetrating salt. So the non-penetrating salt, they bind the wood micelles only through polarizability effect. They are not penetrating into the micelles. And we then investigated the binding efficiency, what's the effect on the persistence length, on the flexibility of the chain. So you see here, when dealing with bromide here salt compared to chloride salt, we have a decrease in LP, means the chain becomes more flexible here when increasing here the binding efficiency. This is for this non-penetrating salt. If we compare with penetrating salt is, for instance, sodium salicylate. So salicylate ions, as shown here in red color here, this salt can penetrate here in the interior of the micelles here, and this affects again the flexibility. We found here LP values around 23 nanometer, so the system becomes even flexible here. So basically, we used the high frequency data here for these systems to monitor the variation of the persistence length as a function of binding efficiency. So all these studies were published here. And then we also try to answer some questions which make debate in the literature since many years ago, how to explain, for instance, variation observed in zero shear viscosity as a function of here salt concentration, keeping the surfactant concentration constant. It is well known in the literature that you have a huge increase in viscosity and decrease, for instance, when increasing the salt content. This for both system with penetrating and non-penetrating salt. And to explain this huge change in viscosity, there is two explanations in the literature. Some people say you have change in micellar length when passing here the viscosity maximum, or you have a structural change from linear to branch micelles. And we answer these questions by performing cryo-temp measurement experiment first. This in collaboration with Professor Danino in Israel. We have shown by cryo-temp that below here the viscosity maximum, we have formation of linear micelles, and the decrease here of viscosity after maximum is due to branch micelles here. Here you see on the picture branch points here, which occurs. So basically, we answer that this huge viscosity upturn here is due to a structural change from linear to branch and not to a change in the length of the micelles. Similar observation for the second maximum here. I will now just focus on the first maximum viscosity. So with DWS, what we have done, we have measured systematically the variation of G0, the elastic plateau module, the persistence length, also the scission energy as a function of salt concentration. Basically, we follow here this salt concentration, and all the results confirm that we have a structural change from linear to branch here. And specifically, the variation in the elasticity of the system. So here is shown for the system with this penetrating counter-ion. This is the first viscosity maximum in blue. And at the same time here below, you see the variation of the G0, the elasticity of the system. And you see that below the viscosity maximum, we have an increase in G0. This corresponds to an increase in the length and the entanglements in for linear chain here. But after the maximum, the viscosity decreased, but the elasticity G0 still continue to increase. So this is due to the fact that you have formation of this branching point, which contribute to the cross-linking density. So we have not a decrease in micellar length after the maximum viscosity. Similar observation has been done for non-penetrating counter-ion here. The viscosity decrease here is due to formation of branching here, but effects here are less pronounced here. So these studies have been published also here, and we also investigated surfactant mixture. We mixed here long chain surfactant with short chain surfactant and investigated the effect of adding this core surfactant chains length on the persistence length, scission energy, and different other parameters here. And here what we found, so we did also the high frequency measurements using DWS, and we found that the persistence length here, as you can see for one system or for some other system, is decreasing when adding short chain surfactant into the mixture here. And this is due to the fact that by adding short chain surfactant, the micelles become less compact, less stable. Therefore, LP is increasing, but also we have observed that viscosity, relaxation time, and elasticity decreases also. So this was also published. So all this publication and this study on worm-like micelles performing DWS makes the industry, would say, curious. So we were contacted with a company. It was basically 3 companies: Covestro, BASF, and Wintershall, and they design new surfactant for rains oil recovery, and they have problems to measure the rheology properties of this type of surfactant. So we use DWS to measure it, and one results we get is concerning the persistence length. Again, from you see here the high frequency measurements we get for this new surfactant LP around 600 nanometer, which is quite stiff compared to more conventional surfactant, where LP is more between 10 and 100 nanometer. So I would say DWS was quite successful for the investigation of worm-like micelles. Second application is on biopolymer and protein solutions here. So in that case also, we use DWS to get information about rheology, structural information, but here also conformational information. And one system we investigated was hyaluronic acid solution. So in that case, we also measure persistent length, which was 7 nanometer, and compare with literature data they found using X-ray neutron scattering 4 to 6, 7 to 10 nanometer. So it's quite working well also DWS for this polysaccharide solution here. And we then investigated what's the impact of the hyaluronic acid concentration on LP, also how the ionic strength impacts the persistent length and the temperature of these solutions here. And finally, also, we verify, we say, the concentration dependence of different here parameter we measure with predicted scaling concept here. So what's coming out is shown here. So first, we have seen that the persistence length is independent of the hyaluronic acid concentration. The LP here is also independent of temperature, and LP also is in good agreement here with the theoretical prediction. You see here the line is what is predicted theoretically by the so-called ODI, this OSF theory. Basically, this is what is predicted theoretically, and you see our points here corresponds quite well with theoretical predictions here. And concerning the scaling concept here, we then compare the exponent we obtain experimentally concerning the specific viscosity, relaxation time, plateau module, G0. We compare this exponent here with theoretical prediction made by Revichan and Dogen here for polysaccharide in the high salt limit, and the same is for neutron polymer in good solvent. And we see that the viscosity parameter, viscosity exponent, and the relaxation time exponent, it deviates from this theoretical, I would say, predictions. G0 not, it fits quite well. So we explain here this deviation by the formation at high, let's say, hyaluronic acid concentration due to the formation of aggregates of polymer chain here. We expected that at this high polymer concentration, we have hydrogen bonds which occurs and make the hyaluronic acid chain to aggregates here. And this has been, would say, confirmed by DLS experiment here. So here from DWS, we get information about flexibility, but also conformational here information. Quite similar study have been made with alginate. Here, in that case, we study the effect of alginate concentration on the viscosity, relaxation time G0, and persistent length, but here in different solvent. We investigated the behavior in water, in PBS, which is a physiological solution, and DMEM, which is basically a cell medium here, typical cell culture medium. So we have different ionic strands. So we measure LP here on the right graph, and in all cases, we find that LP is independent of alginate concentration, ionic strength, and temperature. But we found here differences into the conformation. We compare here also the scaling laws obtained for the specific viscosity here between the three different medium here. So the blue one is for DMEM, the red one is for PBS, and the black one in water. You see that in water, the alginate behaves with an exponent close to what is expected for a polymer in good solvent. So it has a good solvent behavior. But in DMEM, in the cell culture medium, we have a deviation. We have a higher exponent, which is much closer to what is obtained for a polymer in theta solvent here. So basically, alginate in DMEM, we have, would say, chain-chain interactions here, which is not the case in water and in PBS here. So we get here this alginate conformation information from DWS measurements. We have also investigated so-called hydroxyacetylcellulose HEC in water solution. Here also there is a debate whether the morphology of this material is a linear flexible polymer or it's a more rod-like fibril. So here also, and go a little bit faster, we measure the DWS in red here at high frequency, and you see here the frequency domain. And from the high frequency domain, we can predict that this type of here polymer behave like a polymer flexible chain in good solvent here. Again, information about the conformation of this chain here. And also we get information about the relaxation time. We can measure at very short time. Here we are close to 1 millisecond. We can measure here the short relaxation time. This also has been measured using not only DWS in that case, but self-made rheometer here. So basically from the DWS measurements, we also, for the first time, measure and not fitted some relaxation time data here. So this was concerning, I would say, these HEC solutions here. Last example, we also investigated with DWS protein filament here. It was keratin K8, K18. It looks like fibrils like that, filament like that, and can form such kind of network. And here also, basically from high frequency measurements, we measure for that system the persistence length. Not only we did also some other viscoelastic properties, but one important information from these measurements was to characterize the persistence length, and we found what is expected for this protein system, that they are much stiffer than worm-like micelles, for instance, or polysaccharide solutions. We have persistence around here 650 nanometer here. It also work here for this system, but here you have to see that we use as tracer particle polystyrene coated with PEC particles here. Yeah, last example here, we also investigated amino acid. This L-lysine mixed with this salt here, we can form such hydrogels. And here the DWS was used basically to study the effect on temperature of this type of gels here. And here we monitor the variation of we plotted here the variation of the correlation function measured using DWS as a function of temperature. Here we vary the temperature, and basically the would say short times measurements here are would say independent of temperature. So basically the elasticity of the system stays constant when increasing the temperature. But we have seen at a longer time here, which corresponds to long-range particle diffusions, that this range depends of temperature. So basically, increasing the temperature decreases the relaxation time of the chain which compose here the gel here. So it was also working good here, DWS, to monitor changes with temperature here for this type of gel. And now some application on thermosensitive materials. So thermosensitive materials is when at room temperature the solution was liquid and heated at 35 it becomes gel. So one advantage we take from DWS is to characterize this solid-gel transition temperature. So the system we investigated here is silica. It's a ternary system: silica, pyrronic, and starch. And for these systems here, we compare the solid-gel transition determinant using classical rheology, shown here, with DWS. And we found in both cases the same, would say, transition temperature. But I have to say, with DWS, it's much more fast and much more easy to do these measurements here. And in that case, we didn't add tracer particle into the solution. We used the silica particles, which are already in the solution as the tracer particles here, because your solution, as you can see here, is already opaque or turbid here. And also, we measure the kinetic of transition here, also by DWS. We preheated our chamber at 35 degrees and then put our sample, which was stored at 20 degrees, and we see the fast transition of here the correlation function from within 2 minutes, the gelation occurs here. But what you see also with DWS is after 2 minutes, the correlation function still continue to deviate to become slower here. So this means you have aging. So this also, you have then a fast kinetic and a slow kinetic. So this has been able to characterize by performing DWS measurements. The last example is on clay suspensions. So clay suspensions looks like such kind of pellets here. They are disc with a diameter 25 nanometer. They are negative loaded here. And on the face here, they can be positive or negative loaded. And this type of pellets can interact and form different type of structure or gels, you would say. And it's well known that these so-called laponite clay particles or gels, they have also aging effect. So this is something which has been done long time ago by LS instruments and follow the aging effect on these samples. It was working quite well. You see J prime here is increasing over time here. And this is one possibility to do with DWS. And now we use DWS to investigate it, to see if we have differences between the, would say, attractive gels that can be formed with these pellets here, or the repulsive glass here that also can be formed, depending the pH in the solution or also the electrolyte here concentration. You can play with that to form different types of gels or repulsive glasses here. And DWS here, by adding as tracer particle titanium dioxide particles, you see that this is the J prime here. We have good agreement between mechanical measurements and the DWS here. This is the high frequency regime here for J prime here. J double prime here also, we have good agreement, but we see that at high frequency, all the J double prime curves converge. So basically with a slope which stays constant, which is discrete quarter slope in any cases, independent of soil concentration and pH here. So this means that this would say bending mode here of the single clay mineral layers are independent of the types of gels we have here. So with that, I conclude my presentation. So I show many examples where DWS was working well. So, but I would say here the main message is that we find good agreement between mechanical rheometers and DWS method. DWS is a powerful technique characterizing mechanic structure, conformation, and dynamics of various complex materials. Also the dynamics of solid gel transition and aging effect. Main advantage of DWS it's a small sample volume used, less than 1 milliliter, rapidity of measurements, 5 minutes, and you can reach very high frequency regime where you can extract structural and dynamic properties. It's also very sensitive to small changes, for instance, temperature and pH. Some drawback of DWS, it doesn't provide rheological information on a local scale, only ensemble averaging. And also, the surface chemistry of the tracer particle and specific interaction of the tracer with individual components of complex fluid are also an issue and can have a severe effect on the observed particle motion. So this also you have to take care about interaction of tracer particle and the medium here. Finally, I have to thank my collaborator, academic, as well as industry partners, and thank you for your attention, and I feel free for questions. Thank you.